Howdy. We are Group 30. I am Kushagra Jain. My teammates are Sidharth, Anil, and Mounika Balivada, and we are going to present the paper titled Re-Architecting Distributed Block Storage Systems for Improving Random Write Performance. To start with, let's dive back into history. The picture you see on right-hand side is from 1956, and this man is carrying a 5 MB drive. This drive used to weigh 2,000 pounds and was available for $3,200 per month for rent. Why I bring this up is because I want to highlight how storage was the major performance bottleneck back in the day. People had knowledge of algorithms and fast algorithms, but the performance used to take a toll when it came to how to access or how to perform fast read and write operations and have enough storage capabilities at affordable prices. Fast forwarding to the present century, we saw hard disk drives, which were a major improvement in terms of affordability and amount of storage we could do, but they performed not so well when it came to fast read and write accesses, which like for applications like gaming and video editing, which gave way to solid state drives, which are one of the fastest available, commercially available and affordable storage devices, and they perform pretty well when it comes to read and write operations for applications like video processing and gaming, which are very fast paced. But still, a lot of applications still see a performance bottleneck when it comes to them using these devices. And that's why researchers feel that the performance bottleneck has shifted from being a storage device problem to being a software problem. And one solution which they suggest is to give maximum CPU utilization to the software applications to be able to realize the full potential of these storage devices. Though this solution performs well when it comes to standalone storage systems or software applications running on standalone storage systems, but when it comes to a distributed storage system environment, this solution does not scale well because distributed storage system environments need to perform network tasks or some other tasks in addition to storage tasks, which give them significant CPU utilization overhead when it comes to completing those tasks. Plus, it has multiple layers of software modules for each input-output transaction. So that also like adds to the amount of latency they experience because of the architectural design of these softwares. And even industry-leading distributed storage system environments like Ceph are not able to overcome these issues. That's what the authors in this paper are trying to analyze, that how such an industry-leading distributed storage system environment like Ceph has some underlying software architecture issues, the software design issues, which leads to performance bottlenecks. And this is somewhat how they try to define the goal of this paper, that they want to construct a distributed block storage system that can provide exceptional random write performance by redesigning the existing Ceph architecture. So before diving deep into how they perform certain experiments to or certain analysis to come up with underlying issues in the software design, which they try to overcome later, I would like to briefly explain what Ceph is, because they build their solutions on top of Ceph. So Ceph is nothing but an open source distributed storage system, and it gives you or it provides services like block storage, object storage, and file storage. So I'll briefly explain what these are. So file storage is something what you see in your operating systems. Like we have directories and subdirectories, and we store data in like a hierarchical structure. Uh, Block storage is a step ahead of file storage. It is used for large and structured data. So say if you have a large file, you can split the file into different blocks with unique IDs and store them on different disks. And when it comes to object storage, it's mostly for large and unstructured data. You define them as an object by giving it an ID, have some metadata defining the data and the actual data you want to store, and you store these objects in the disks. So coming back to Ceph. So Ceph basically has two major components. One is the interface, which helps you make requests and receive responses for your object storage, block storage, and file storage. And the second part is the actual Ceph OSD cluster or storage cluster, which consists of storage nodes and monitor nodes. So monitor node is nothing but a node which consists a global map of what object is stored where on or on which node, so that it becomes easier when you perform a read and write operation to know the location of the object. And and a normal storage node is the one which contains a module called an object storage device daemon, which helps you perform the storage tasks. So I'll break down how the object storage device daemon looks like. It basically consists of three major modules. The first module is the messenger module, which consists of a pool of messenger threads, which try to perform message exchange tasks like Say, for example, you want to send a replication message to a different node and receive an acknowledgement back from them. So all these communication happen through the messenger with the help of messenger threads, and a pool of these messenger threads is what the messenger module contains. The second module they talk about is the object storage device core, which consists of a pool of PG threads. PG stands for partition group. Why partition group is, as I mentioned, like block storage divides a file into different blocks, and even for object storage, you can group your objects into some kind of logical partition. So these kind of partitioning tasks are done by PG threads, and they perform two important functions. One is to inform other nodes uh, to do replication and to inform the local backend store to perform the transaction. Coming to the third module, it's the backend object store. The major responsibility it has to is to make sure that the transaction is durable. That means the data what is stored in the object store should persist over time, and it needs certain maintenance tasks like compaction. So the idea behind compaction is that whenever a write request comes, you either create a new object node or you overwrite current object. But to do so, you can group certain objects together so that you have some free objects available to write to, or to store the new incoming data. And that's like that's similar to garbage collection, but in garbage collection, you get rid of the data in a certain memory location instead of grouping them together and freeing it. So yeah, moving forward to the motivation part. So they perform certain analysis to which help them come up with the shortcomings of the existing safe architecture. So to brief you about the analysis, what they did is they took original Ceph and they took three modifications of Ceph, which are called RTC V1, RTC V2, and RTC V3. V1, V2, V3 are different versions, and RTC basically stands for run to completion, which basically means that it's preemptive, or you can say that a task will not start execution unless a new task will not start execution unless the current task completes itself. So what modifications I did was, so in RTC V1, it basically performs all the tasks like message processing, replication, transaction processing, object storing, and maintenance tasks, which original Ceph performs, but it only does it on a single thread. RTC V2 performs all the tasks which RTC V1 performs, except for object storing tasks, and RTC V3 does not perform object storing as well as transaction processing tasks. So when they compared the latency performances of these different versions, they figured out that RTC V3 performs the best with roughly around 0.8 millisecond of latency. But according to them, it was still not good enough considering that Ceph uses SSDs. And considering that RTC V3 only performs message processing and application processing, which is mostly required by write operations. A significant part of this latency and poor CPU performance is due to the write operations, which they try to analyze further. Why would that be happening? And then later on propose what all they can do to improve this problem. So based on those experiments, they claim that there are three possible reasons or three major reasons why those performance issues or latency issues occur in Ceph. The first one is that in Ceph, the low latency tasks, the tasks which need fast responses, and the best effort tasks which need CPU resources are tightly coupled. And if they want to reduce latency and they want to improve CPU performance, they need certain optimizations, but those are different kind of optimizations. And since these two kinds of tasks are tightly coupled, they cannot perform those two different kinds of modifications separately. Uh, the second issue they uh, or claim is that Ceph uses different kinds of threads like messenger threads and PG threads for different kind of purposes. So when a lot of requests comes in, or a fast-paced kind of request comes in where they need to frequently context switch between threads, the context switch cost can be huge, leading to poor performance and higher latencies. The third reason they mention is that Ceph uses a tree-based backend data store that requires costly operations like compaction and garbage collection. And also they want to have logs on data to ensure that different processes do not access the data at the same time to maintain consistency. And that leads to higher latency and poor CPU performance. So they try to overcome these issues by suggesting some implementations, and I will leave it to Siddharth to explain those to you. Thank you.
All right, so now the Kushagra has mentioned the issues that the authors are trying to solve. I will go over the design and implementation where they're suggesting a new architecture. And the new architecture is basically like there's three major points that they have in that. So the first one is decouple the operation process. The second one would be prioritized thread control. And the third one is CPU efficient object store. So I'll go over it one by one and I'll try to explain it further. So the first one is decoupling the operation process. So this is the system that Ceph has right now. This is the input output path that Ceph has right now. So NVM here would be a non-volatile memory, which could be something like just a battery-backed RAM system. So we won't have a lot of storage space, but it'll be pretty fast. So the goal is to kind of use it for storing logs and things like that, caching and things like that. SSD would be where most of the SSD would be where primarily the data is stored, permanently the data is stored, right? So the system that they have right now is that the client would be sending the request in, and the storage node would interact with the SSD and get the data or write the data, and they would ask the replicas to do the same. They would send replication messages, and the replicas would also interact with their SSDs, and they would send back the acknowledgement. And only once the primary storage node receives all the acknowledgement, it's only at that point that it responds back to the client. So the thing is, there are two certain type of tasks here. So the interaction to the SSD, this part actually could be done in a batch manner. If it was possible, it could be done in a batch manner. Because instead of writing it one by one, if you store all of it together and write it together, that would be pretty efficient. But the issue is that the request to the client, so that would be this part, that should happen as fast as possible because the client wants the response as fast as possible, right? So there's two different kind of tasks here, so which is heavily coupled together, which is why right now it's not as efficient as it could be. So if there was a way to decouple this section and this section, which would be the interaction with the SSD, if there was a way to decouple these both, then the top part of it could happen in a latency critical manner, and the interaction with the SSD could happen in a batch manner. It happens in batches. So to kind of understand this a little further, we can use an analogy. So the analogy here would be that let's say a client wants some information, or the client wants to store some information. So the system that exists right now is that the client would walk up to the front desk and say his request, and the person at the front desk would go into a room at the back, maybe like a library with a lot of books in there, and they would like get the information or write the information, whatever they have to do, and they would ask their replicas to do the same. The person at that front desk would also go back to the library and do the same, and once he gets the acknowledgement back, at that point he'll respond back to the client. This is the system right now. So the suggestion to improve the efficiency is that if the person who's sitting at the front desk is able to respond back to the client without having to go to the SSD each time, then the interaction with the client would happen really fast in like latency critical manner. For that to happen, the person at the front desk would need to have some data with him, like some information with him. So say he has a book where he can store some information, right? So using the information stored in that book, he's trying to respond back to the client. So when a client comes in to store an information, instead of going to the SSD and writing it, or in this case, going to the library and finding the book and writing it there, instead of doing that, what the person at the front desk does is he writes it to the book that he has at the front desk, right? And he'll ask his replica to do the same. So the front desk person at the replica would also write to his book at the front desk instead of going to the SSD, right? And he would respond back to the client. And when another client comes in to read information, instead of going to the library and finding the information, he first goes through the book he has. And if he has enough information at the front desk to respond back to the client, right, he doesn't need to go back to the library. He can just respond back to the client immediately. If in case he doesn't have enough information in his book, because the book he has would be pretty small compared to the huge library behind, right? So if he doesn't have enough information in his front desk place in that book, then at that point he has to go back to the library and get the information. So this is kind of like caching in a way. And when the information gets too huge in his book, at that point, he would asynchronously, that is, he would go back, or maybe ask someone else to go back to the library and kind of write down all the information, transfer all the information from the book into the main storage system. This is just like an intuitive idea of what the authors are suggesting. This is the new suggested architecture, which you could compare with the old one. And you can see that in the old one, this was part of the input-output path, the writing to the SSD or reading from the SSD, whereas in the new suggested architecture, this happened asynchronously. So this would be the latency critical path of input-output, which happens as fast as possible, and the client is served as fast as possible, and this happens in an asynchronous manner. And to do this, like I said, there should be a book at the front desk, right? So in this case, that would be data structures. And the data structures that they use is they would have an operation log and they would have an index cache. So an operation log would just contain all of the requests that come in a sequential manner. And the index cache is just a hash map that can be used to search through the operation log efficiently, just to find the request related to a specific object, right? And with this context, we can just briefly go over each operation. So let's say it's like a write operation. when there's a write operation, instead of going to the SSD and doing things with the SSD, you just write the operation request to the operation log, and you make the necessary updates in the index cache, and that's it. You can then ask the replica to do the same, and then you can respond back. And in a read operation, you first go through the operation log that you have at the NVM level, and then if enough information is found, at that point you respond back to the client immediately. And if there's not enough information, then you go to the SSD and get the information, and maybe you can update your operation log along the process. And then there would be the flush operation. The flush operation would be that when the data in the operation log gets too heavy, too big, at that point, you write it to the SSD. So when it exceeds a certain threshold, you write all the information to the SSD, and then you delete it from the operation log and the index cache. And the recover also would work like with the replica. So if the primary, or if a storage node fails, at that point, the replica, on identifying this, they would write all the information they had in their operation log to the SSD to make it persistent, right? And then they would assign a new storage node to cover for the failed one, and the new storage node would synchronize with the replica to get the information to update its operation logs and index cache, so that it can take the place of the failed storage node. Okay, so in my explanation of the input-output path, I didn't explain about threads, but threads are very important. So that was one of the biggest bottlenecks in the previous system, according to the authors, right? The fact that you have to constantly context switch between threads during an input-output path, that would take a lot of time, especially in a situation where things should be fast. So now that we have decoupled it, threading can be done in a much more effective manner. So the suggestion that the authors make is that for this new system, you need basically two kinds of threads. So the first type of threads would be the priority threads. Now the priority threads is responsible for handling the portion highlighted within the red box here. So that would be the low latency part, right? And so that should happen as fast as possible. And because of that, the priority thread would have their own dedicated core. So they won't have to battle for cores. So there won't be context which is happening there, right? So that will increase their efficiency, and they'll decrease the latency hugely. And then there would be non-priority threads. And non-priority threads are the one who are responsible for doing the asynchronous flushing between NVM and SSD and things like that. And that doesn't happen often compared to the priority thread. And it doesn't need to happen like really fast. It happens in a batch, best effort manner, right? So non-priority thread wouldn't have their own dedicated code. They would just share the remaining codes, and they won't be invoked unless they're needed to. The non-priority thread would just be invoked when a flush operation is required, or when you actually have to go to SSD to serve the client. And that's the point when non-priority thread wakes up. And then we have the CPU efficient object store. So in this section, so we didn't talk about the object store until now. Object store would be what would happen inside the SSD, right? Or like right on top of the SSD. But how do you store the information in SSD and things like that? So in CPU efficient object store that the authors are suggesting, their main concern is to try and prevent host side write amplification. Host side write amplification happens when, like, say the client has one write request, but to just carry out that one write request, the storage node has to do 5 writes. They'll have to update the metadata. They would have to move data around to make space for the new data, things like that, right? So the number of writes got amplified at the host side. We don't want that to happen. And to prevent that, they use an updation technique where they're updating in place so that we don't have to write a lot. They use pre-allocation techniques. Pre-allocation techniques is like they already allocate the blocks where the data would go in, right? So if they do that, and if they're able to initialize a lot of the metadata, then you won't have to write all of that metadata when the actual write request comes in. So they kind of allocate it beforehand, before the request even comes in. That is pre-allocation technique. And pre-allocation technique can happen only if the storage system already knows the size of the data that will come in. So there should be a fixed size for the object. If it's dynamic, then you can't pre-allocate it. So, but luckily for the distributed block object storage systems like Ceph, the size is fixed, so that's fine. And they also use the NVM for storing metadata, because metadata updation, at least at a certain level, would happen. And instead of doing that at SSD, if you do it at NVM, you can save a lot of time there, right? So they use the NVM system for storing metadata and for storing the cache of metadata, basically. Another thing is that they are partitioning the disk space, and they're partitioning it in such a way so that each non-priority thread only handles one partition. So there won't be multiple non-priority threads handling the same partition, so you won't have to keep track between them and make sure that they're not clashing with each other and things like that. So here, each non-priority thread only deals with one logical section, one partition. So there's a nice even split between them. So that's about all of the suggestions in there, all the key points in their new architecture. And to see whether it actually improved the performance, I'll hand it over to my friend to explain the results and evaluation.
I'm going to discuss about evolution for the prototype discussed by Sidharth. For evolution, the paper has used Crimson, Cep's updated architecture, the 1502 version. To measure performance of the design prototype, proper environment setup is needed. So total of 9 machines are used for performance evaluation. 4 of them are used for storage nodes, while 5 are used for clients generating workloads. These 9 machines are connected with a 100 GB network. In addition, partitioning is done. The storage system is partitioned into smaller blocks, and each block is assigned to a specific node or server. This allows for better load balancing and reduces contention when multiple nodes try to access the same block simultaneously. The NVM SSDs are partitioned into 4 logical partitions for better load balancing. Before each experiment, we perform secure erase commands on every SSD to return them to their original performance state. Going to benchmarks, we evaluate the block storage service and object service of Ceph using FIO and YCSB benchmarks. The following parameters are measured and compared with the original model and ideal model. IOPS. IOPS is input-output operations per second. It is the number of read and write operations that can be performed by the storage device per second. The higher the IOPS, the faster the device can read and write the data. The next one is latency. It is the intuitive one, the time delay between a request for data and the response received from the storage system. The next one is utilization of logical CPU cores. A percentage of time that a given logical CPU core is busy processing task or executing task. The 3 models are compared in the paper for each of the performance metric that we are going to do in the next slides. The first one is original system. The original system is the existing distributed block storage system in Ceph architecture. The next one is proposed. This is a proposed prototype based on Ceph architecture. The next one is the ideal one. This is the system which has no overhead, a system in which there is no additional time, CPU cycles and memory required by computer system to manage and maintain storage system. Moving on to the next one, we are going to evaluate all these benchmark evaluations in the next upcoming slides. They are small random performance, host side write amplification, YCSB, partition scalability, worst case latency. I'm going to discuss about small random performance first. It is the ability of a storage device to perform small random read and write operations. It is usually measured in terms of IOPS, CPU usage and latency. FIO is used to measure this. Flexible IO tester is a popular open source benchmarking tool used to measure the performance of storage devices and systems. There is huge performance improvement if we see the results. The proposed achieves 820K IOPS with latency of 1.1 milliseconds. On the other hand, original achieves only 181K IOPS with a latency of 4.3 milliseconds. These results implies for both random write and random read operations. And also the CPU utilization is highly reduced. Moving to the host side write amplification, it is a phenomena where the amount of data returned to a storage device by the host computer is amplified on the storage device due to the way the data is managed and stored. The figure shows number of bytes returned to a storage and the number of bytes user issues. In original system, the number of bytes is 3 times the number of bytes user issues. But in the proposed system, it comes down to 1.4 times because writing an object requires IOs to metadata area in CPU efficient object store also. However, it is less than original thanks to the in-place update disk layout. The next one is YCSB. It's Yahoo Cloud Servicing Benchmark. It's a framework designed to evaluate the performance of NoSQL databases. It provides standard set of workloads for insert, read, update, and delete operations that can be used to benchmark the performance of different databases. To evaluate proposed design under real workload, we run YCSB on the client nodes using block device on different workloads. So we have mixed workloads, read-only workload and read modify write workload with different ratios like 50 is to 50 read and write, 95 is to 5 read and write, and or read only, and another mixed workload and read modify write workload. So the result shows the proposed write latency is significantly lower than the original, and also the IOPS values are significantly increased. Moving to the next one is partition scalability. We run the performance test with varying the number of shared partitions in a OSD. The performance is improved every time the number of shared partitions increases. This implies for both random write and random read operations. The next one is worst case latency. So the 95th percentile latency is measured. The worst case latency is the maximum time that a system takes to respond to the given request. The figure demonstrates the 95th percentile latency when we issue a mixed random workload. The latency grows considerably depending on the number of entries in an operation log. To conclude, the paper proposed a new architecture that addressed the problem of poor random write performance. In compared to the native Ceph, the given prototype yields 3 times higher IOPS for small random write workloads. It also achieves 60% CPU load reduction. We also observed significant improvements that can be done to the proposed system. The first one is improved data tiering. Ceph currently supports data tiering, which allows data to be automatically moved between different tiers of storage based on usage patterns and performance requirements. However, there is still room for improvement in this area. For example, Ceph could incorporate machine learning algorithms to optimize data placement and movement based on usage patterns, workload characteristics, and other factors. The next one is faster recovery from node failure. Ceph is designed to be highly fault tolerant with data replication and erasure coding mechanisms to protect against data loss. However, in the event of node failure, recovery can be slow and resource intensive. Ceph could potentially improve recovery times by incorporating more efficient recovery mechanisms or by optimizing the recovery process for specific workloads. That's all. Thank you.